When we think of concrete, what comes to mind? Solid, right? Permanent, the very definition of unchanging. But what if I told you that's not the whole story? That the concrete all around us, in our sidewalks, our buildings, our bridges, is actually constantly, secretly in motion.
Yeah, we even have that phrase set in stone, right? It's supposed to mean something is permanent, it's not going anywhere. But when it comes to concrete itself, the reality is, well, it's a lot more dynamic. The surprising truth is that concrete moves. A lot.
Okay, just take a look at this arch bridge. It wasn't built with that dip in the middle. No way. Over decades, its own incredible weight has caused it to slowly sag, to deform. It's almost like it's an unbelievably thick, slow-moving liquid. This phenomenon is a huge part of our story today, and it's called creep. And trust me, it's just one of the hidden forces we're going to dive into.
All right, so first up, let's talk about a force that you've absolutely seen the effects of, even if you didn't know what it was called, and that is shrinkage.
So, what exactly is it? Well, to put it simply, shrinkage is what happens when concrete starts to lose water to the air around it, as it dries. When that water leaves the system, the concrete actually contracts. It gets smaller. The absolute best way to picture this is to think of mud cracking under a hot sun. That's basically shrinkage in action.
And that process is exactly what leads to those familiar cracks we see everywhere. See, what happens is the surface of the concrete dries out and shrinks way faster than the inside, which is still wet. So you get this internal tug-of-war going on, building up all this tension until something's gotta give, and pop, a crack forms to relieve all that stress. This, by the way, is precisely why engineers put those lines, those control joints into sidewalks. They're basically telling the cracks, hey, if you're gonna happen right here where we can manage you.
Okay, so that's shrinkage. Now let's move on to our second force, which is, well, it's a little more mysterious. This one isn't about drying out. This is all about pressure over a very, very long time. This is creep.
So creep is this gradual, permanent change in shape that happens when concrete is under a constant load. Remember that sagging bridge? Its own weight, just pressing down day in and day out, year after year, is what causes this slow flow. A good analogy is if you put a really heavy book on a block of foam and just leave it there for a while. Even when you take the book away, that dent is still there. With concrete, that deformation is permanent, and it can take decades.
So let's make sure we're clear on the difference here, because it's super important. Shrinkage, that happens just from drying out. It doesn't need any weight on it at all. Creep, on the other hand, absolutely requires a constant, sustained load. But, and this is the really fascinating part, they have a common link. Deep down, at the microscopic level of the cement paste, both of these things are caused by the movement of water. It's either water leaving the concrete entirely, or it's being squeezed from high-pressure spots to low-pressure spots within the concrete itself.
Okay, so if concrete is always moving, shrinking, and creeping, how in the world do we build anything that actually lasts? Well, this is where some seriously clever engineering comes into play. Because the goal isn't to completely stop these forces, you can't. The goal is to manage them. And engineers have a whole toolkit to make this happen. For one, they can tweak the actual recipe of the concrete. They can add more stable stuff like stone and sand. That's called aggregate. Or they can mix in these tiny reinforcing fibers. Then, on a bigger scale, they actually design the whole structure to account for the movement, creating things like those control joints we mentioned to basically tell the cracks where to go. Let's actually visualize why the recipe is so important. Think of it like this. It's the cement paste, the glue that holds everything together. That's the part that actually shrinks and creeps. The aggregate, the sand and stone, is pretty stable. It doesn't really move. So it stands to reason, right? If you have a recipe with a ton of paste, like you see here, you're going to have a lot more potential for movement.
And here's the solution. It's kind of brilliant in its simplicity. You just maximize the amount of stable aggregate. By doing that, you're basically creating a rigid internal skeleton inside the concrete. The paste still wants to shrink and move, but that strong skeleton of rock and sand just holds it in place. The relationship is actually super simple. The more aggregate you pack in there, the less the whole thing moves. It's a simple but really powerful principle.
Okay, now for another really clever trick. Fibers. We're talking about adding tiny steel fibers right into the concrete mix. Now, a simple straight fiber, yeah, it provides some resistance, but it can eventually just get pulled out as a crack tries to form. But check this out. A hooked-end fiber, this is a total game changer. That little hook acts like a tiny anchor. Before that fiber can get pulled out, the hook has to physically straighten out, and that process absorbs a huge amount of energy, which helps hold the whole thing together. So cool.
So, when you put this all together, what's the big takeaway? It's really about a fundamental shift in how we have to think about building things. You learn pretty quickly you can't fight the laws of physics. You have to learn to design with them.
Because the real genius of modern structural engineering isn't trying to make concrete that's perfectly still. We know that's impossible. The real skill is being able to predict exactly how much a bridge is going to sag or how much a building column will shrink over its entire lifetime. We're talking 50, even 100 years. And then you design the structure from day one to be able to handle that movement safely.
And listen, these movements are not trivial. We're talking about a typical piece of concrete shrinking by maybe 300 to 600 microstrains. Now, I know, microstrain sounds incredibly tiny. It basically means parts per million. But think about it this way. If you have a 100-foot-long bridge beam and it shrinks by just 500 microstrains, that's a third of an inch of movement. Doesn't sound like much, but when you scale that up across a massive structure, those tiny little changes add up to huge, very real forces that absolutely have to be accounted for.
And really, that brings it all home, doesn't it? Our world is literally built out of concrete. And the only reason our buildings, our bridges, and our dams are safe is because generations of engineers have learned to respect and design for these incredibly powerful, invisible, slow-motion forces.
So the next time you're walking on a sidewalk or driving over a bridge, just remember, it's not as static as it looks. In a way, it's a living structure, slowly breathing and shifting in ways we can't even see. And that leaves me with one final thought for you to chew on. What other so-called permanent materials in our world are also secretly on the move?